Every moment of this transit was monitored, revealing that the gas giant's impact on 3I Atlas is unprecedented in all records of modern astronomy. Jupiter has just intercepted a visitor from another stellar system with a mass of 1 billion tons, subjecting it to the most crushing gravitational force in our cosmic neighborhood. The result of this interaction has left the scientific community on high alert. 3I Atlas displays characteristics fundamentally distinct from those recorded just a few days ago. This enigmatic object, the strangest ever identified in our solar system, crossed Jupiter's domain at an impressive speed of 41 miles per second. Furthermore, a second celestial body has just entered our system. Almost ignored by the general public, it may possess a link to the first object that defies astronomers' understanding and generates profound technical discomfort. Let's get straight to the point, but before we begin, don't forget to like the video and subscribe to our channel. After all, what was Jupiter's real effect on 3I Atlas? On March 16, 2026, upon reaching a distance of 33.3 million miles from the planet, the object didn't just perform a common flyby. It plunged into the most hostile gravitational field in the solar system, surpassed only by the Sun. With a mass 318 times greater than Earth's, Jupiter acted like a cosmic press upon the interstellar visitor. Its gravitational field doesn't just attract, it stretches, compresses, and tests the resilience of anything that gets close enough. What happened to 3I Atlas during those hours is known as tidal force. As the object approached Jupiter, the side of 3I Atlas facing the planet was pulled with more strength than the opposite side. This difference in attraction on an object approximately 1.6 miles wide creates internal tension. Think of it like wringing out a wet towel. The object is squeezed and stretched simultaneously. For a natural comet made of loosely packed ice and rock, this type of stress can trigger surface fractures, increased outgassing, and, in extreme cases, partial fragmentation. But here is what makes this different from any comet transit we have ever studied. Jupiter's gravitational reach, what scientists call the Hill radius, extends exactly 33.2 million miles from the center of the planet. This is the invisible frontier where Jupiter's gravity overcomes the Sun's pull. 3I Atlas passed within less than 0.1% of that exact line. At this limit, Jupiter's gravity was doing something specific to 3I Atlas's trajectory. It was acting as a gravitational slingshot, curving the object's path and adding a velocity component that will carry 3I Atlas out of our solar system faster than it would have departed on its own. Jupiter essentially gave it a push toward the exit door. This is the part that makes scientists lean forward in their chairs. The precise degree of this trajectory curvature depends on the object's mass distribution. If 3I Atlas is a uniform natural comet, the curve should follow a predictable pattern. If its mass is distributed unevenly, the way it would be if it contained dense internal structures that a natural comet would not have, the post-transit trajectory will be measurably different from what models initially predicted. This post-transit trajectory data is being analyzed right now. And here is the detail that Avi Loeb, former head of Harvard's astronomy department and former member of the President's Council of Advisors on Science and Technology, flagged even before the transit occurred. If 3I Atlas released any object during this encounter, something that received the correct velocity adjustment to enter a stable orbit around Jupiter, it would represent what he called a clear technological signature. Since the physics of a natural comet breaking apart cannot produce the type of precise velocity shift required to park something in Jupiter's orbit at 41 miles per second, the probability of any random interstellar object hitting that gravitational target by pure chance is less than 0.5%. The Juno spacecraft, currently in orbit around Jupiter, was watching. So were JUICE, the European Space Agency's Jupiter Icy Moons Explorer, and ground-based observatories across the planet. As of the writing of this script, no new object has been confirmed in Jovian orbit. However, image analysis takes time, and data is still being processed. Jupiter has 95 known moons, many of them tiny, dark, and difficult to detect. A new object the size of a city block in the correct orbit could take weeks to confirm. Here is something that puts the entire 3I Atlas situation into perspective. A new paper co-authored by Loeb and researchers from the University Observatory Munich, Valentin Thos and Andy Burkert, produced the most precise mass estimate of 3I Atlas to date. Their conclusion is that 3I Atlas has a mass of approximately 1.1 billion tons. For comparison, the first interstellar object ever detected, Oumuamua, discovered in 2017, had an estimated final mass of about 11,000 tons. 3I Atlas is 100,000 times more massive than Oumuamua. Now here is why that number is so concerning for astronomers. When scientists study the size distribution of asteroids and comets, both in our solar system and in the galaxy at large, they follow a well-established pattern. Smaller objects far outnumber larger ones. For every giant rock, there should be hundreds of thousands of smaller ones. The math is consistent and reliable. Therefore, if 3I Atlas is 100,000 times more massive than Oumuamua, basic statistics say we should have detected at least 100,000 interstellar objects the size of Oumuamua before seeing something the size of 3I Atlas. We haven't detected any. The Vera C. Rubin Observatory, which became operational in February 2026 and is capable of generating up to 7 million celestial alerts per night, was designed specifically to find objects like these. If smaller interstellar objects existed in the numbers that statistics require, Rubin should be finding them regularly. So far, the smaller objects are not showing up, which leaves two possibilities. Either our distribution models for interstellar objects are fundamentally wrong, or the objects we are detecting, Oumuamua and 3I Atlas, do not follow natural size distributions because they are not naturally occurring objects. Loeb has been direct about this. The mass discrepancy alone, setting aside any other anomaly, is enough to make the artificial origin hypothesis statistically competitive with the natural one. In a 9-month interval, our solar system was visited by an object carrying billions of years of chemistry, displaying geometric precision in its jet structure, tested by the most powerful gravitational field in the solar system, and leaving questions that our best telescopes and brightest minds still cannot answer. A second object, possibly unrelated or perhaps not, is now days away from a close pass by the Sun that will confirm if it is an unusual natural comet or add another layer to a story that refuses to have a simple ending. The Rubin Observatory will find more of these objects, that is certain. The question is what those objects will look like when we find them. If they follow the size distribution we expect from natural processes, the 3I Atlas anomaly becomes easier to explain. If this absence of smaller objects persists, the statistical evidence that we are facing something out of the ordinary will be impossible to ignore. If this content brought you relevant reflections, leave a like, subscribe to the channel, and join the discussion in the comments. Do you believe Jupiter's gravitational pressures exposed some characteristic in 3I Atlas that changed your perception of it? I will be following all your opinions. If you know anyone fascinated by astronomy, be it a friend, colleague, or family member, send this content to them right now. This is certainly the update they won't want to miss.